And Kong, you're going to do the intro today.
I mean, whatever. Okay, let me then give me a few minutes. Then you will do the questions.
Okay. Should I start?
Oh no!
Wait till the. Oh, wait! We start at 5 after.
Oh no! Yeah, exactly. Yeah.
Yeah, no. So MIT classes begin at 5 after the hour. Okay. So,
okay.
Okay. And yeah. So we generally wait till 11:05 or so. Yeah. Well, no, it's good that they're getting another 1.2 though. That's yeah. Do they have the building for it at the University of Zurich already, or is it?
No, as far as I know, they still have to build something. That's why I don't really understand. But also Basel would also have needed to build something. But in Basel, a new building was erected anyway, so this would have been easier, in my opinion. But
yeah.
But both we realize that this is not now. It's we are in public, right?
Okay, that's all right.
That's all right for you, of course, Bob.
Well, it's good news. All right, that
Right.
there will be others. Okay, so
Yeah.
mhm. Yeah.
Gunnar, can I just ask you a technical question?
technical question.
Yeah, I'm just curious because I'm interested in buying a frequency synthesizer, and then I came across this company yesterday. It's called Anapico in Switzerland.
Which one?
Anapico.
No, I don't know.
Okay. Maybe can I just share screen for a few minutes, for 2 minutes? Or okay, never mind. I will send you. I will send you an email later.
Yeah.
Yeah,
Send it to me too.
Yeah.
Yeah. Yes. Hi, Art.
Morning, Bob. Morning, all.
Hey there, Art. How you doing, buddy?
I am fine. Other than the fact that marathon training has started.
Will they let you out to run in New York now with the virus? And
Well, I happen to be in Ohio, but yes, in New York, you can get out and run as well.
Mm-hmm.
The humidity is a bigger problem than the virus.
Well, that's okay. Yeah. Mm-hmm.
The main problem with the virus is I think it's now, a month ago, they were very confident they'd be running the marathon in November. And now I would say it's 50-50 at best.
Yeah. They postponed the Boston to September, October.
Right.
I just wonder if they're going to have it, considering everything that's going on. So, yeah.
On the other hand, a friend of mine says the best thing you can do is train for the marathon, but then not run it, because you get in great shape, but you don't destroy yourself by actually running the race.
Well, that's good. Yeah. Mm-hmm. That's true. Yeah.
And let me know if you need August 20th for your meeting, because I can probably free that day up.
Okay. All right. Well, as soon as we're done today, I'm going to try and get that organized. I finally heard from everybody, from Anne this morning, for example. So, yeah. So Hartman says, after my knee surgery, the doctor said, run the marathon, but don't train.
Oh. Ui, 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 ui.
Well,
That sounds like
seriously.
malpractice.
Pardon?
That sounds like malpractice.
Yeah, but I woke up in a room with 5 people who practiced for the marathon, who had the same surgery.
Okay, Kong, you want to start the introduction now? Okay,
Oh yeah, sure.
okay. let me-
Yeah. Okay. Good morning, good afternoon, good evening, everyone, wherever you are. So welcome to our Zoominar series again. And then just before I introduce our speaker today, Gunnar Jeschke, I would just tell you the usual thing that I've been telling everyone. So if this is your first time here to attend our series, feel free to sign up for our mailing list. And I mean, I can imagine, because when we invited Gunnar to give a talk here, and then I expect some people from the EPR community will be interested in hearing this. And then so we might expect some new attendees here. So for the new attendees, so if you're interested in more of our talks, I don't know how long this will last, feel free to sign up for our mailing list. And also if you are interested in the past, in listening to the talks that were given by the speakers that we have hosted in the past, you can find the details on the Griffin Group website, which I put in the chat room. And if you have any questions, you can type your questions anytime during the talk or towards the end. But I would like to ask you to use the Q&A function, which you can find at the bottom of your Zoom interface. So try not to use the chat room. You can say hi, but don't ask the question there, because it's likely that we will not be able to read it. Okay, so I will introduce our speaker today. So it's our honor, and also we are delighted to be able to host Gunnar Jeschke today. And then when I first wrote to Gunnar a couple of weeks ago, I asked him, hey Gunnar, would you have some interesting topics that you would like to share with us? And then Gunnar said yes, he actually has several topics. And then because I've always been very interested in listening to his research topics and his talks. So I asked Gunnar, why don't you just give 2 talks? I mean, try to combine 2 topics and give a 1 hour, maybe 40 minutes or 1 hour long lecture. And then he said yes. So we appreciate that, and we are very grateful that we have Gunnar here. So Gunnar, he started his chemistry diploma in chemistry in TU Dresden. And then after that, then he joined after Schweiger Group in ETH for his PhD. And then after Schweiger, you probably know that he wrote a very, very famous book, Pulse EPR, which to me is still one of the most important reference book or the Bible for the Pulse EPR if you want to know more about it. Then after his PhD, then he took a position in Max Planck Institute for Polymer Research in Mainz, Germany, as a group leader. And after that, then he joined University of Konstanz as a professor. And then after that, then he joined ETH Zurich as a professor. And then I was talking to him. He told me that of course, we knew that he was the head of the department of the chemistry and applied biology. And still, until today, he remains the wise head, which he will be the wise head for another 3 or 4 days. So it's our pleasure, and we would like to welcome Gunnar Jeschke to present his topic today. So the floor is all yours, Gunnar.
Thank you very much for the kind introduction. And as Kong already said, these are 2 topics, 2 projects, but in the end, they come together. This will be the last slide before the acknowledgement. So this will be a talk about relaxation, maybe, or maybe something which is not exactly relaxation. We will see this. And the people who had the initiative in the 2 projects were Janne Sodberg from my own group. She worked on this dynamical decoupling part. And Mantas Ximenes from Vilnius University, he brought this problem of the methyl tunnel coupling to us, so basically the spectra which brought us to this idea, and you will see this later in the talk. So basically, what I want to talk about is electron spin coherence, and why do we still lose it at very low temperature, and is there some way to recover it or to keep it alive for a longer time? And let's start with what was already known before we started with these two projects. So all relevant motion, if we talk about nitroxide spin layers, is frozen out at about 50 K and below. But then one still has quite strong relaxation. And if the electron spin is sufficiently diluted, we found this may be 50 micromolar or something like that, then nuclear spin diffusion is the only channel basically which covers electron spin decoherence. And in a way, this was already known since the 1970s. And the mechanism was imagined like that. So if you excite the electron spin, you will change the hyperfine field at the protons. Then the proton bars is no longer in equilibrium with the environment. And this non-equilibrium magnetization of the nuclei of the protons can diffuse in the bars due to the flip-flop term of the dipole-dipole coupling. And then they said, well, this diffusion means that we have a stochastically fluctuating hyperfine field due to the flipping protons. The protons make flip-flops, and because they have different couplings to the electron spin, you have some fluctuation of the hyperfine field at the electron spin. And then you can treat this and you can get contribution to the relaxation rate, to the transverse relaxation rate of the electron spins, if you assume that the protons are homogeneously distributed in space and that all this is applying. Now, what you can also say, and this was all well known already, that there is a certain range, a certain shell, a diffuse shell about the electron spin, which mainly contributes. So protons very close to an electron spin, they do not contribute so much because they are decoupled from the proton bars. If you do dynamic nuclear polarization, you know this concept. And if they are very far away, then this field fluctuation at the electron spin has very small amplitude because the dipole-dipole coupling decays with R1 over R cube, and then they are also not relevant anymore. And there's some shell where this is relevant. Now, here comes the first spoiler. We have to correct this picture a little bit. This idea that diffusion leads to a stochastically fluctuating hyperfine field at the electron spin, I think is physically not really justified. But at the same time, we will see that this idea, the concept and the assumption of this diffusion has indeed contributed to the understanding and has been productive for developing approaches of characterizing this relaxation. Now, another correction that I have to make right at the beginning is this idea that protons are homogeneously distributed. They are not. And let's think about water as a solvent. Then you have a very short distance between the two protons on the same water molecule. And the next proton on the neighboring water molecule is much further away. So you have a strong nuclear dipole-dipole coupling between these two protons, and all the other dipole-dipole couplings between protons in other molecules are much weaker. And you will see that this makes a difference. So the approximation of homogeneously distributed protons in the environment in the bars is not a good one. And there's another effect. If you have methyl groups in the environment, not only that you then have three very close protons, but then you have tunnel splitting, and we will see that this tunnel splitting is also changing things. Okay, now, why were we interested in this topic? So you may know that we work on distance measurements between electron spins, and there's a very well-established pulse sequence for pulse steer that we usually apply. And in 2013, the group of Jack Fried, Peter Borbert, and Elka Georgieva, they suggested that one can measure for a longer time, that one can reduce the relaxation by spacing the pulses equally, like in a Carper-Cell sequence. So this basically, the observer sequence is the simplest Carper-Cell sequence with only 2 pi pulses, whereas the normal conventional 4-pulse steer has asymmetric delays. And because of this symmetric delay idea, one has to introduce another pulse. This introduces complications, but what you can see if you use this sequence is that you can observe the deer trace for a longer time. You still get the same distance distribution, but it can be very useful. Now, when Peter Borbert and Jack Fried and Elka Georgieva, when they introduced this 5-pulse steer, they argued that it is better because the electron spin decoherence is not an exponential process. It's more or less a Gaussian decay approximately. And the Gaussian decay corresponds to diffusive motion, and Carper-Cell basically was suggested for refocusing in the presence of diffusive processes. And they computed it, and it's all very fine. And we also see this if we measure on temporal radicals in water glycerol. It's not really a Gaussian decay, the Hahn-Echo decay, but it's certainly not exponential. And by using this Carper-Cell idea, we get a much longer time window for measuring the dipole-dipole couplings between electron spins than in the Hahn-Echo or the 4-pulse steer. But then we did the same experiment on small membrane inserting peptide. And it is known that in lipid bilayers, the relaxation of the electron spin is faster. But what's more, it's almost mono-exponential. So the blue dashed line is mono-exponential decay, and the black line below is the relaxation that you see for the Hahn-Echo. And still, if we apply the 5-pulse steer sequence, we get a longer time window, a slower decay. This cannot be understood by the idea that the decay is Gaussian because it is exponential here. So we wanted to understand this better. So we looked into this whole problem of dynamical decoupling. Now I have to tell you what dynamical decoupling is. Dynamical decoupling is basically Carper-Cell and similar sequences applied to prolonging the coherence lifetime of electron spins. And the term dynamical decoupling was coined in the quantum information processing community. And we will come back to other concepts from this community later. So they need to keep the electron spin coherence alive for a very long time to apply their quantum gate operations. And they found out that this can be done by multiple refocusing. This increases the lifetime. And now they usually do it in semiconductor type materials with a low concentration of dopants. We have much more messy systems. We have glassy solvents, and in these glassy solvents, we have labeled biomolecules. And we wanted to see how these concepts apply to our samples and how far we can get by applying these concepts to our samples. And we wanted to study this systematically. So first we did it on model systems where we can deuterate both the methyl groups on the spin label itself, or we can deuterate the solvent. Now the deuteration, let me go back. The deuteration will change things because in this rough approximative formula, you have the G value of the nuclear spin, or if you wish, the gyromagnetic ratio, which is much smaller for deuterium. You also have a spin quantum number factor, but if you substitute the protons by deuterium, you make this contribution much smaller. And this is indeed what we see here. If we go from the completely protonated system to the completely deuterated system, you have to look at the time scale here. This is 150 microseconds. This is only 50 microseconds. Then we prolong the relaxation times. Now, before I talk about the comparison between the different systems, I first want to introduce one of these pictures in more detail. If I can, let's see. Okay, now hopefully you now see this plot. And here, this is the normal Hahn echo, the black one. And the first thing that we see is that the normal Hahn echo decay already has two components. There's a fast component and a slower component. I will show this in more detail on another example on the next slide. You also see it here. There's a fast component and a slower component. This is already car per cell with two refocusing pulses. And now if I go from the Hahn echo to 2 pi pulses, to 3 pi pulses, to 4 pi pulses, I prolong the relaxation time or the coherence lifetime. On the other hand, I also lose something. I lose intensity in the beginning because each of the pulses that we apply to electron spins is lossy because we have insufficient excitation bandwidth. This is one problem. There are also other problems that, for instance, you excite forbidden coherence on the nuclear spins. And for these reasons, we lose a little bit if we apply more pulses, but we prolong the coherence lifetime. There's also a different type of dynamical decoupling sequence introduced by Götz Uhrig. And he computed for a certain case where the frequencies that cause the coherence, the fluctuation frequencies, if you wish, if they are small, then one can compute a better pulse spacing than the uniform pulse spacing of car per cell. And Uhrig derived this pulse spacing. And indeed here for the protonated label in protonated water glycerol, we see that the Uhrig sequence, the red and orange shades, is a little bit better than the car per cell sequences with the same number of refocusing pulses. Not a big deal, but a little bit better. Okay, now let's go back to the overview again. By looking at all these cases, we can assign the contributions. So this fast component, as you see here and that you see here, this vanishes when we deuterate the methyl group. So this fast component probably comes from the methyl group. And what I already said, if we deuterate a solvent, we get the much bigger effect, a much longer prolongation of the coherence lifetime. Okay, now let me come back to this question of the two decays. And here I show this on the case of the protonated spin label in deuterated water glycerol, car per cell with 5 refocusing pulses. So before we did this, the decay shapes or the Hahn echo decay was generally fitted by the stretched exponential function. For Gaussian, you would have a 2 here. For an exponential, mono exponential, you would have a 1 here. And this is treated as a fit parameter, and you get something, often you get something between 1 and 2 for Hahn echo. Even in the case of the Hahn echo, as I showed you on the previous slide, this does not always work. And we just extended this model, or Janne just extended this model to 2 stretched exponentials, and then the fit is much better. You see this in the residual. You may wonder about this residual, why this is so lopsided. It is known that nuclear modulation, electron spin echo envelope modulation, just goes down. So you have to fit the maxima of the nuclear modulation if you want to characterize relaxation. And this is what was done here. And then with this sum of stretched exponentials models, you get a very good fit of the data. And of course, I showed the example where it is very clear that you need this model, but we checked it, Janne checked it on all the samples. Sometimes you can fit with a single stretched exponential, but most of the times she needed the sum of stretched exponential models. And then you can look at the parameters of this model as a function of the number of refocusing pulses. And the first thing what you see is what we want to do. We want to prolong the phase memory time, so the lifetime of our coherence. And the funny fact is, at the beginning, we didn't understand this. We just saw it. It's linear in the number of pulses, both for the slow component, which is related to the solvent, and for the fast component, which is related to the metal groups. Here, you may wonder whether this is really linear, but here it's quite clear. We also see that the stretch exponent doesn't change so much. For the metal groups, it's almost mono exponential. For the glassy solvent, the water glycerol mixture, it's not mono exponential. It's even hyper Gaussian, if you wish. Stretch exponent larger than 2. And we see very similar behavior. This is a purely organic matrix, purely aromatic protons, orthoterphenyl, and this is water glycerol. The qualitative behavior is very similar. Quantitatively, there's a difference. In orthoterphenyl, we have longer relaxation times than in water glycerol. This was already known before, but here we have it in a very precise, quantified way. And again, here in these plots, you see that uric is a little bit better than car per cell. In water glycerol, you cannot really say that. Okay. Now, we use a concept that was introduced by the quantum information processing community not very long ago to get a better understanding of this dynamical decoupling. And what they introduced is noise spectroscopy. There were similar ideas around in magnetic resonance before, but it's a little bit different from what was done before in magnetic resonance. So what they say, based on this idea that you have these stochastic fluctuations by the flip-flop terms, if you assume that these nuclear spin flip-flops lead to pure dephasing, so you have no longitudinal relaxation, only decoherence, the refocusing pulses are perfect, and the noise, the fluctuations of the hyperfine fields are Gaussian, then you can quantify all this in terms of a spectral density function. which you call the noise spectrum. And you can reconstruct this spectral density function, this noise spectrum, from your data. And then you have to think, how do you get the information? And the information you get because the pulse sequences act like filter functions on this noise spectrum. Because they introduce this refocusing. And the more pulses you have, so this was Hahn, the blue ones are the Carr-Purcell, the red-orange ones are the UX sequences. And if it gets lighter, you have more pulses. This shifts the spectrum, or this shifts the filter function. And if you increase the total length of the pulse sequence, you also shift the filter function. So this is a logarithmic scale here. So by looking at different times and with different frequencies, you can cover quite a broad range of frequencies and filter parts of the noise spectrum. And by doing the right mathematics, you can reconstruct the noise spectrum from the decays W as a function of t that you have measured. So these are the experimental data here. You take the logarithm, and then you have an integral equation here, and you have to invert this integral equation for computing the noise spectrum. And this worked quite well for the quantum information processing people, first because they have rather perfect refocusing pulses, they have very narrow spectra, and they can apply a lot of refocusing pulses because they have very slow relaxation. We can't. And actually, I wanted Janne to do this noise spectroscopy, and Janne found that this was not at all easy. And the problem is that we have a small number of pulses and that the inversion of the logarithm of the experimental decay to the noise spectrum is an ill-posed problem. Now we can work with ill-posed problems because we also have an ill-posed problem if we make a distance distribution measurement. So direct inversion fails, we know that. So Janne first applied regularization. And the non-negativity restraint, this is the standard that we also do for the distance distribution. But even this turned out to be unstable against high frequency noise. But then Janne had the idea that she could just fit not the original data or use the regularization not on the original data, but on the sum of stretched exponentials models. And in a way, you can say this is adaptive wavelet denoising. We do a denoising and also suppression of the nuclear ECM by fitting the sum of stretched exponential model. And then after this, we apply Tikhonov regularization. And this then gives reproducible noise spectra, and you can also get some uncertainty estimate for the noise spectra. And then you can understand by, again, looking at the different labels and the different matrices that we have, where the contributions are coming from. And you have a matrix contribution from this glassy solvent that goes, let's say, up to 50 kilohertz or maybe 80 to 100 kilohertz. And you have higher frequency contributions that come from the methyl groups. I mean, in a way that these are higher frequency contributions is trivial because we know that they lead to a faster decay. But to really get the shape of this spectral density function, you need to do this. Okay. Now we learned a little bit more from the quantum information processing community. The linear increase of the phase memory time with the number of pulses that we have seen independently was already known, also since 2011. Sometimes one should read the literature. So this arises from the small cutoff frequency of the noise spectrum. So if you think in this idea of the noise spectrum of the spectral density function, you can find that this should be the case. And also the higher cutoff frequency for water glycerol that we saw on the previous page. Okay, no, we don't see this on the previous page. So, sorry, I don't have the OTP data on the slide, but the OTP has a lower cutoff frequency. You see this basically here in the solid state NMR spectra. In this seminar, I should show solid state NMR spectra. So the OTP has a narrower static solid state NMR spectrum, and the width of this spectrum is determined by the dipole-dipole coupling between the protons, which is stronger in water glycerol than in OTP. This leads to the higher cutoff frequency in water glycerol, and this explains why the dynamical decoupling efficiency is lower in water glycerol. And the lower cutoff frequency also explains the slightly superior performance of uric decoupling in protonated solvent for the orthoterphenyl. Okay, now we have one more concept from the quantum information processing community, which turned out to be very good for understanding. This is cluster correlation expansion. And actually, this was not taken up by us originally. This was taken up by Marina Kveda's group in Zagreb. She did the first work on organic radical systems in EPR. And later by Stefan Stoll's group from University of Washington at Seattle. And what they did rather recently, they used this concept to predict the decay. So these are not fits. The red lines are not fits, they are predictions. They made a molecular dynamic simulation of water. And then they carried this cluster correlation expansion, which I will explain in a minute, up to two nuclear spin clusters. And they get a very good agreement of the prediction with the experimental data, actually too good, because the experimental data are also water glycerol, and the computations that they did is just water. Now, what is this cluster correlation expansion? What you can show generally, that the time domain signal is the sum of products for disjoint clusters of nuclear spins. So for each cluster of nuclear spins, you can compute the signal for the electron spin by spin dynamics. And you will see that the nuclear spins, the contributions from the nuclear spins, they are products. So you have this product. And then if you have disjoint clusters, you should have a sum. But then they said, okay, we can get rid of the sum in an approximation. We assume that we don't have disjoint clusters, and then everything gets more simple, because if you just have the product, you can again take a logarithm and get a sum out of it. Okay, now the point about this is, if I have a cluster with k nuclear spins, I have a k+1 spin system. So 2 nuclear spins and the electron spin is a 3-spin system. And the computation by the Stoll group shows that 2 nuclear spin clusters are sufficient. Then we can compute this analytically. So in a way, we can give something back to the quantum information processing community, because we also know a few tricks that they don't use usually. And one of these tricks is product operator formalism. So basically, the quantum information processing community expanded the problem to 3-spin systems for us. If we solve the 3-spin system, the rest is just product of 3-spin systems. And the 3-spin system we can solve analytically by product operator formalism. This may sound surprising, because the nuclear spin Hamiltonian is not diagonal. And this term does not commute with the hyperfine Hamiltonian. So you cannot straight apply product operator formalism. But this problem of non-commutation was solved already in the 1990s for computing electron spin echo envelope modulation spectroscopy with product operator formalism. So what you do is the following. You first apply a transformation into the eigenbasis of this Hamiltonian. Then you evolve in the eigenbasis of the Hamiltonian, where the Hamiltonian is diagonal, where all the terms of the Hamiltonian commute. You go back to the Zeeman basis, you apply the pulse, you go back to the eigenbasis, you do the second evolution, and you go back to the Zeeman basis for detecting. And this transformation for this Hamiltonian, which diagonal is this Hamiltonian, can be computed analytically. It's just two by two blocks, which have to be rotated by the same angle in opposite directions. And the angle can be computed from the nuclear-nuclear dipole-dipole coupling, which we know, and from the difference of the hyperfine couplings. And then you already see that the mixing of the levels will be maximum if the nuclear-nuclear dipole-dipole coupling just matches the difference of the hyperfine couplings to the two nuclear spins. So here you have a cartoon. This is the electron spin. It has different hyperfine couplings to the two nuclei. The nuclei are coupled to each other by dipole-dipole coupling. And if this coupling is the same as the difference between these two couplings, then you get maximum mixing of the levels by this Hamiltonian, by this flip-flop term of the Hamiltonian. You can compute everything. This is the angle by which you have to rotate state space. And then you can compute the electron spin coherence that you have after a single refocusing. So we first do it for the Hahn echo for a single refocusing. But of course, if we have repeated refocusing, we can use the same, we can apply the same formula. It's again only a product. So we have a modulation depth, which corresponds to this state space rotation angle. And we have a modulation which has only two frequencies. And these frequencies are the nuclear zero quantum frequency. Let me go back. It's just this frequency. Which results, it's basically Pythagoras for the difference of the hyperfine coupling and the dipole-dipole frequency of the nuclear spin. Okay, and then already on this three-spin system, we can understand dynamical decoupling, because if we apply this formula for the total length t with one refocusing pulse, we get this black curve for the Hahn echo. If we do it for n equal 2, we make two refocusings with a shorter time corresponding to Carper cell 2, we get this evolution. If we do 3, we get already this evolution. So by 3 to 5, it's almost completely suppressed. And this is already the so-called, well, I would call it the sour spot, the anti-sweet spot, where we have this matching between the difference of the hyperfine couplings and the nuclear-nuclear dipole-dipole coupling for the distance that you have for protons in water in some arbitrary orientation. Okay, now this is not really relaxation. This is just nuclear pair modulation. It's a nuclear pair ECM effect. So why does it look like relaxation? So if you would have just a three-spin system, then the coherence would recur at then this product of the nuclear zero quantum frequency and tau is 2 pi or 4 pi or 6 pi. So it recurs completely at some times. But if we have many of these pairs of these water molecules in the vicinity of the electron spin, then this does not recur anymore, because all these frequencies are slightly different. And then we have destructive interference. And the decoherence basically is destructive interference of a nuclear pair ECM. It's not stochastic flips of a hyperfine field, if you wish. Now, if we remain in this picture, then we can compute everything. We just have the distance, and then we have 3 Euler angles for orientation of the water molecule, and we have an angle between the oxygen electron axis and the magnetic field. So the picture that I show here has a very long electron oxygen distance. This is the typical case because most of the water molecules are remote from the electron spin because the number of water molecules at a distance r scales with r squared. But if you are far away, then the hyperfine couplings to these two protons are very similar because the two distances are very similar and also the two orientations of the proton electron vector are very similar. Then you have a very small difference of the hyperfine coupling, you get a very small mixing angle, and you don't get much of a contribution. So the major contributions come from water molecules at distances below 30 angstrom. And if you look at the sum projection, even below, the maximum is even below 10 angstrom. So in principle, from this data, I could also predict, I could do the same as Stefan Stoll's group, Liz Canary did. I could compute or predict the decay functions, but this I cannot show today because these data are very new. Now I'm already talking for quite a long time. I will make the rest a little bit faster. So what was also already known is that methyl groups cause faster decoherence. This is already known since the 1990s. If you have methyl solvent, you get faster relaxation than in a solvent that doesn't have methyl groups. And there would be three mechanistic candidates in the picture that we already have. If you look at this cluster correlation expansion, here we obviously have 3-spin clusters in, instead of 2-spin clusters, which should lead to more decoherence. Then we have rotational libration motion that is still active at low temperatures. And for methyl group, unlike for the protons and water, we have methyl tunnel splitting. Now, let's assess these three mechanisms. So the 3-spin part certainly contributes, but it's very unlikely that this explains the very fast decay that we see for only 4 methyl groups in the nitroxide. The libration motion should cause substantial temperature dependence. Can be computed how temperature dependent this is. We don't see this. And the 2-pulse tunnel ECM had already been suggested in the 1990s. But this paper does it for isotropic hyperfine coupling, so it's not directly applicable. Now, by coincidence, we stumbled over the methyl tunnel ECM effect in collaboration work with the Vilnius group, Mantas Šeimenas. So what they did, they put dimethyl ammonium ions into a metal organic framework. Actually, the Polish collaborators did this. And then they measured ECM spectra to characterize this material. And they got odd signals which are non-magnetic magnetic resonance. So the signals don't shift and the intensity does not change, the relative intensity does not change, even if you change the magnetic field by an order of magnitude. You go from X band to W band and you basically have the same signals. They do vanish when you deuterate the methyl groups. So if you deuterate something else, they don't vanish, but if you deuterate the methyl groups in this dimethyl ammonium ion, then they vanish. Now, I very shortly explain why this leads to an ECM effect, the tunneling. So in principle, if you have a methyl quantum rotor, you have this rotation barrier, and then you have rho librational levels here. And in the ground state, the 3 orientations of the methyl group have degenerate levels. But they don't remain degenerate because you have some overlap of the wave functions in the 3 localized states, and this overlap will mix the levels, and will lead to some splitting. And for symmetry reasons, you have one A state and two E states, and you have a tunnel splitting here. Now, why does this mix with the electron spin? This mixes with the electron spin because the hyperfine coupling breaks symmetry of the threefold symmetry of the metal group. I just put an electron spin not along the C3 axis. And I assume that my three protons have different magnetic quantum numbers. They also have different hyperfine couplings. The three positions have different hyperfine couplings because the distance and the orientation of the electron-proton vector is different. Now, this means that this configuration of nuclear spins corresponding to this rotational state has a different energy than this configuration. I just permuted the magnetic quantum numbers, but because the three positions have different hyperfine energies, this will change the energy between these two states and also between these two states. And this means the electron spin introduces influences the coupling, influences tunnel splitting. We get a mixing between these states, and even the degeneracy of the E states is lifted. And this then, in a similar way as 3-pulse ECM, leads to the generation of tunnel coherence. So the first pulse will generate a forbidden coherence, or coherence on a forbidden transition on an electron spin end tunnel transition. So this transition connects these two different tunnel states, and it connects two electron spin states. And if I apply another pi/2 pulse to the electron spin, then I can shift this coherence completely on the tunnel transitions. So I basically have metal tunnel coherence. This evolves during time t, and then I get the tunnel ECM effect, which is not magnetic because the tunnel splitting is not magnetic. Here you see that this basically works. The simulation is not perfect, but we do see this frequency independence, which we have experimentally. We don't get a perfect fit of the data. We do see a quite good fit of the expected temperature dependence because the tunnel splitting has a temperature dependence, and we see this in our experimental data. And we can also check the dependence of the modulation amplitude on the first interpulse delay, and this also basically fits. What didn't fit is when we did hyperfine decoupling, we expected that this split line would collapse into one very narrow line, and this didn't happen. Okay. I can't talk anymore about solving this problem. We thought this might be coupling between the two metal groups. This would be a long story for which I don't have time anymore. But I can show you the short result of the long story because it's anyway an anticlimax. Treating the coupling is not needed. So here you see the case of a metal group barrier of 10.5 kilojoule per mole without any rotational coupling between two metal groups, which gives this signal. And here you see the case of a lower barrier between the rotational states, between the localized states, and the coupling between the rotational coupling between the two metal groups. And these two modulations are exactly the same if we match the tunnel splitting. So you can't see a difference between these two, which means that our experiment is not sensitive to the separation between the barrier height and the coupling between rotational coupling between metal groups. And this means we can just use single rotor computations. If you want to look how this was done, there's a new paper just out in Applied Magnetic Resonance. Okay, and now I can come to the final slide, which brings all this together. So what Janne did, using the solution for a single metal group, she computed metal tunneling 2-pulse ECM numerically and compared it to the fast decaying component in our data. And for this, she has a fit parameter, which is the tunneling frequency. So she can fit the tunnel frequency by fitting the data. And these tunnel frequencies are in the range where you expect them for a high-end metal group in nitroxide. Because you can compute the rotational barrier by DFT computations. You can compute for this rotational barrier what the tunnel frequency should be. And this is in the right range. It's not exact, but it's in the right range. And what you also see is that if you go to deuterium, it's about 20 times smaller, at least. And this is also what you expect because the heavier deuterons lead to a much smaller tunnel splitting, and the factor of 20 approximately is also something known from the literature. Okay, with that, I would be at the end, and my take-home message is basically the slide which I showed in the very beginning. You have to be, if you talk about the proton spin bars, you have to be careful. The proton spin bars are structured, and this makes a difference in what happens to the electron spin by the coupling two proton spin pairs or two metal groups. Okay, in the end, I want to acknowledge a few people. I already talked about Janne and Mantas, but I want to thank my whole EPR group. Actually, Daniel Klose, who is in the audience, was also involved in the metal rotor part. Andrea Eggeling is taking over from Janne in the dynamical decoupling and metal tunneling part. Our collaboration partners at Vilnius University, Leipzig University, and the Polish Academy of Sciences worked on the, or supplied us with the materials and some of the spectra for the tunneling. Adelheid Goth, Miriam Hößmann at Bielefeld University make the nice model compounds. And Konstantin Zuboulis and Marta Millen worked with Janne actually on other spin labels partially in the dynamical decoupling project. The Swiss National Fund and the ETH financed the project, and I thank you for your patience with a talk that got too long.
Whoops. Can turn my screen on. Okay. Well, thank you very much, Gunnar, for that very inspiring, intellectually deep talk. All right. There are a couple of questions already. One of them goes back to the very beginning from an anonymous attendee, wanting to know the difference between the Carper cell biboom gilt and the Ulrich. That was on the first slide or two.
Yeah, I have to share screen again.
However, yeah.
So it's basically just the spacing of the
pulses, yeah.
Pulses. So for the Carper cell sequence, all these spacings are equal. And for the Ulrich decoupling sequence, there's a formula, which I don't have on the slide, which one can look up. The formula which for a given number of pulses gives the relative delays, so the ratio between the delays TOR1, TOR2, and TOR3. And this was actually optimized for refocusing low frequency noise spectrum or low frequency spectral density function that governs this relaxation or decoherence.
Yeah. Okay, yeah. And the next question from Ilya, he wants to know, is there much hope for simulating long-range coherence dynamics with cluster correlation, with a cluster correlation expansion? All of our attempts have not been successful. It seems that cluster count explodes before it gets accurate.
Okay, so I think I have to give a qualified answer to that. To get it accurate, probably cluster count will explode. If you just do it for getting some understanding, so you see you are not yet accurate, but you can explain a lot of the effect by 2-spin clusters or 3-spin clusters. This you can do. It may depend on the system. I think also here the quantum information processing community is at an advantage. They often work in systems that are extremely dilute, and then it works better. I don't know yet how well this will really work in water. The simulations from Stefan Stolz' group look very good. But then I would have to say that if you use a water glycerol glass 1-to-1, you have quite strongly diluted water pairs. Glycerol has much less pairs, at only 1 pair per molecule, and the molecule is larger. So these are not really the same systems. So there's probably some error compensation in these calculations. So we have to see how well this really works. We can also see this by using our analytical computation, but I did not yet do this because it's so new. So in principle, the analytical computation should also show whether we can phrase this in just the pairs, the water pairs, or whether we need to consider the couplings between protons on different water molecules. And I suppose we have to get quantitatively correct.
So Bjorn Corzelius asked for the 3-spin clusters. Would you need actual clustering in the matrix, or would you not observe the same dephasing of NN coherence if you assign nuclear pairs randomly in a homogeneous distribution? And he modifies that and says better random distribution, not homogeneous. Okay.
Yeah. So no, I think this will not come out to the same. And the reason is that if I just take the proton density in water, and then you look at you just do it randomly, and you look at the distribution of pair distances, then you will have much less short pair distances than in water. And some of them actually will be too short for comfort. Some of them will be so short that you cannot match them by the difference of the hyperfine coupling. And many of them will be too long. So I believe that, but this still has to be checked, but I believe that this distance in the water molecule leads to stronger decoherence than you would have for random distribution of the protons in the solution. But this is something which can be studied by using this formula.
And Art Palmer asked, I might have missed it, what is the duty cycle of the pulses in the CPMG, the pulse length compared to delays?
This, of course, depends because we measure these things starting at a very short delay, and then we increase the delay at the same number of pulses. So we do it a little bit different than you would do CPMG and NMR. In CPMG and NMR, you would measure the whole echo trace at once, maybe hundreds of echoes, depending on how long this lives. And you look at all the echo intensities. That we don't do. We measure only the last echo, and then we increase the delay. And this is how we measure these decays for a given number of pulses. And the shortest duty cycle, the highest duty cycle is probably something like 10%. So the delay approximately 160 nanosecond, and the pulse length approximately 16 nanosecond. And then if we increase the total length of the sequence, then the duty cycle gets smaller. But this is the duty cycle during the sequence. Of course, then the repetition of the sequence is much, much longer. So the total duty cycle cannot be more than 1.5%, because this is what our traveling wave tube amplifier can do.
Yeah. So maybe I misremember, but in the case of a solid, protonated solid, the Uhrig train gives much, much longer decays. Is that right? Than the Carper cell train. I mean, this was the point in developing the Uhrig.
Yes, so actually the improvement that we see for Uhrig over Carper cell is very slight, but in some other cases it's much better.
No. Yeah, no, it doesn't improve it at all, which was kind of, I mean, it's essentially the same as a Carper cell.
It's almost the same. This is also something really that the analytical formula I got last week, second half of last week. In principle, having this analytical formula in hand, it would be possible to optimize the delays by the analytical formula and to check why it doesn't work, or why Uhrig doesn't work as good in this case. So what I indicated in the beginning, this idea, the whole idea which is behind this optimization is these stochastic flip-flops, and it cannot be completely wrong. So this idea of the noise spectrum and the stochastic flip-flops is very productive, but it's not the right thing that the flip-flops are not stochastic. It's a coherent evolution of this three-spin system which can explain the same phenomenon. And then I suppose that maybe the Uhrig optimization is not the correct optimization, or not the best optimization that you can have for this problem. But this has to be checked. I just don't know it yet.
And why don't you look between the pulses rather than just at the final echo?
Aha.
I mean, is the receiver recovery problem?
Yes, it's a receiver recovery problem. It's also, I mean, in principle, because we have the spacing so that we can see the last echo, in principle, we could also see the other echoes. This is a problem of the Bruker spectrometer. So the digitizer is in principle fast, but the transfer from the digitizer to the computer is so slow that measuring the whole sequence, or the whole echo train is worse than measuring only the last echo and transferring the data faster.
Right.
It's a bad problem.
Okay. All right. Well, Kong, do you have any further questions?
Yeah, just a quick one.
Yeah.
You know, of course, like when I saw these flip-flop terms among the protons, then you know that in NMR we do this all the time for the homonuclear decoupling. So I was just wondering, is it possible to put the IF pulses there to homonuclear the protons, like just like what we do all the time for? Is it possible?
Well, this is something we should study. Actually, we had a project where we wanted to study things like that. This is something we should do.
I don't know, FSLG, PMLG, Lee Goldberg or something.
It's harder to combine with other pi-CPR experiments. So at the same time, we want to keep the dipole-dipole coupling alive, or to keep some other electron-nuclear couplings alive. And then it may be difficult with the homonuclear decoupling sequences, but it is going in the right direction. So this should be done, yeah.
Because then you can manipulate in coherence in whatever way you like. They will be quite interesting. Yeah.
Okay, so if there are no further questions, we really want to thank Gunnar.
I think we have one question.
Oh, is there another one? Oh, another one just popped up. Right, yeah, you're right. Is the analytical solution possible if the pseudo-secular hyperfine coupling cannot be neglected?
That's a very good question. Actually, I did the whole treatment for a lecture, for the advanced magnetic resonance lecture script that I prepare. And for that, I took a minimal Hamiltonian and I threw away the pseudo-secular hyperfine coupling so that I can solve it analytically. If the pseudo-secular hyperfine coupling is present, I cannot solve it analytically anymore. So this also has to be checked by numerical simulations, how much the pseudo-secular hyperfine coupling influences the whole thing, this decay that we compute. So what we follow here, and also I checked this analytical computation by comparing to numerical computation, we have to do the same for adding the pseudo-secular hyperfine coupling in this computation where I have all the orientations of the water molecules. It's easy to do. And then to see how much this differs. This we have to do, but it cannot be done analytically.
Okay. Okay, so now there are no more questions, at least for the moment. All right. So again, Gunnar, thank you very much for this presentation today. And in a couple of weeks, what the date will be, August, about 13th, something like that. I mean, when's our next?
10th of August.
10th of August, yes.
Yeah.
10th of August, we're going to have Sophia Hayes and Chen Yang talking about his new DNP soup simulation program. So we'll continue in 2 weeks. And then after that, we're going to have a couple of breaks. One for the ISMAR conference in Japan, in Osaka. And then the following week, there's the hyperpolarization meeting in Lyon. And then we will reconvene then in September at some point, right? Okay, so again, Gunnar, thank you very much for a really very nice talk, okay?
Thank you for the invitation. Thanks.
See you guys and see everyone in 2 weeks then. Bye.
Bye.